Alright guys, I got a fancy problem for you today, and by fancy, of course I mean awesome, and by awesome, of course I mean, yeah, it's got induction and derivatives in it. This is going to be pretty sweet. Alright, here we go. Letter A, find f to the nth derivative of x for n equals 1, 2, 3, and 4. So here we go, we're going to start off with our f of x. We know that f of x is equal to x e to the ax. So our first derivative, we're going to do the product rule here. So I've got x, so u will be x, v will be e to the ax, so du will be 1, and dv is e to the ax times the derivative of the inside, which is just a, so a e to the ax. And so then, you know, I've seen this both ways, it doesn't really matter, but u times dv plus v du, which is 1. Now I notice that there's a common e to the ax there, so I'm going to rewrite this as e to the ax times ax plus 1. And there you go. So there's the first derivative. We can go ahead and we can do the second derivative the same way. Again, we've got u, which can be e to the ax, and v, which can be ax plus 1. And you can go through a similar process. I'm just going to go ahead and write them down here to save us a little bit of time. So when I did this, I ended up getting a e to the ax plus 2. And then I got the third derivative. So when n equals 3, I got a squared e to the ax plus 3. And then when I did the fourth, and you can do IV there if you want, or you can put 4 marks, it doesn't really matter, equals a to the cubed, e to the ax, not to the cubed, just cubed, and then ax plus 4. Alright, so take your time, pause the video, work through those, make sure you're comfortable with derivatives. Hopefully you get the same thing as I did once you simplify. Okay, now at this point, we're going to go, okay, we've done letter A, check. Now we'll do B. Conjecture a formula for f nth derivative of x for all positive integers. Alright, so what I see a couple of things here, right? I see that I've got these a's on the front, right? A to the first, a squared, a to the third. Now there's not one here. Of course, that really just means it's probably a to the 0. If I'm keeping with the pattern, 3, 2, 1, 0. So that would make sense. The a to the 0 is 1, so it doesn't really need to be there. Okay, so that's one thing I see there. So that would be f nth derivative. Actually, you know what? We're going to need the space later, so let's just do it down here. F nth derivative of x equals a. So when this was the first derivative, it was a to the 0. Second derivative was a to the first, so on and so forth. So to the n minus 1. And then I see e to the ax on all of these. Note that they're all exactly the same. E to the ax, e to the ax, e to the ax. So e to the ax. All right. And then here, you see they've all got ax. So this is ax plus 1, ax plus 2, ax plus 3, ax plus 4. Note that the coefficient, or sorry, the constant here always matches the derivative, 3, 4. And so we're just going to go ax plus the order of the derivative. All right, so there we've got a formula. That's just guessing off of what we have here. So now what we're going to do, of course, is use the principle of mathematical induction to prove our conjecture. So this is where it gets nice and fancy schmancy. We can already check one. We've actually already done one, but let's just go ahead. We'll make n equals 1 just because old habits die hard. So first derivative of x, so we go a to the 1 minus 1, e to the ax plus 1, and we find that we get a to the 0. So we have e to the ax times ax plus 1. And of course, as we already knew, because we created from that as part of our conjecture, it works. So now let's write n equals k. Now we're writing this because we're going to assume for a minute that it works for n equals k. So that just means the kth derivative of x equals a to the k minus 1, e, that is a minus 1 there. No, don't do that. Not a good idea. k minus 1 e to the ax times ax plus k. All right, now we're going to show that it works for n equals k plus 1. So if I put that in, f to the k plus 1 of x equals a to the k plus 1 minus 1 e to the ax and ax plus k plus 1. All right, so we just need to show that this works. Now, I've got one formula here. Now I just need to find out how to get the k plus 1 derivative. Well, that's just the derivative of the kth derivative, right? It's just one more derivative. So what I need to do is I need the derivative of this function right here. So let's take the derivative of the kth derivative. So I'm going to say that a to the k plus 1 e to the ax is u1. So u equals a to the k minus 1 e to the ax. Okay, and then I'm going to say that v is ax plus k. And from here, it's pretty easy to work it out. Same derivative that we just did so many times over there. That's why I said, you know, it's a good idea to just work it out, figure it out, make sure that you can get it, because you're going to do it again here. So a to the k plus k minus 1 is a constant multiplier. It's a coefficient for the e to the ax. Of course, the derivative of e to the ax is a e to the ax, because it's just e to the ax times the derivative of the inside. All right, now that simplifies because it's a to the k minus 1 times a. Remember, when we multiply, we just add those exponents together. K minus 1 plus 1 is just k, and so I get a to the k e to the ax. And then, of course, this one's even easier. dv is simply a, derivative of constant is 0, and then it's just the coefficient of the x there. So now if I put all that together, then I end up getting that the derivative of f, the k plus 1 derivative, or the derivative of this, is u, so a to the k minus 1 e to the ax times dv plus v times du, which was a to the k e to the ax. And we need to show that this is equal to what we have up there above. Now if I rewrite this a little bit, I'm going to end up with a to the k e to the ax times ax plus k plus 1. And we note that here, again, I have that right here. I've got a to the k minus 1 and a, which is going to give me a to the k. So if I take out a to the k e to the ax, then I'm left with, well, that's everything here. So I'm left with 1 plus ax plus k. And notice that these two are exactly the same, except the 1's in a different place. Just move the 1 over ax plus k plus 1, and I get exactly the same thing that I started with. So therefore, I can make the statement that because it works, we assume that it works for n equals k, because it works for n equals 1, and it works for n equals k plus 1 if it works for n equals k, therefore it has been proven. Okay, QED. I don't remember what that means, but somebody that knows a little bit more will probably be able to answer QED, but that's what we just say, therefore it's been proven. Okay, now this is just because if it works for n equals 1, that's k, therefore it works for k plus 1, which is 2. But if it works for 2, then it then works for 3, because 2 plus 1 is 3. And if it works for 3, then n equals 3, then it's got to work for 3 plus 1, so it works for 4. And so therefore it goes on and on forever. And therefore, by mathematical induction, we have proved that our conjecture is true. That's all, folks.